Okay, anybody have any questions about, I think I assigned one problem, right? Everyone okay? Okay. So here's where we are right now. We're still today, I think should be the last day of just going through this derivation stuff. But we did the undamped oscillator. And we just got that was a sinusoidal, back and forth motion. When we looked at the graph, it just ended up being a cosine term. It could also have an added on sine term if you use different boundary conditions. If your time equals 0 represented a different part in that motion. And then we went to the damped oscillator. And this is one where you still have the mass, you still have the spring, but now you also have a dash pot, a viscous damper, and that is a constant C. And it led to the differential equation x double dot plus C over m times x dot plus k over m times x is equal to 0. So that's the governing differential equation. And we assumed a solution x of t equal to e to the lambda t. And using that assumption, we got the following roots. We got lambda is equal to negative c over 2m plus or minus square root of c squared minus 4km all over 2m. So those are the two roots. And we had three sort of fundamentally different cases of this. The first one was the overdamped case. As you can imagine, that is where the c is big. So that's the case where c squared is greater than 4km. And what we got for solutions was so after using the boundary conditions, we got that x was equal to, let's see, well, that's ugly. Okay, so we got that solution. And then the next case was, okay, and what did we qualitatively, like how would you describe the overdamped case? This is a case where the oscillations are killed immediately because the damping is so high, but it doesn't get back to equilibrium very fast. Okay, so this is slower to get back to equilibrium. Then the second case is the transition case, This is the one that's most useful for control systems when you're trying to develop damping to remove oscillations. This is the case where c squared is equal to 4km. And we got two repeated roots here. And the solution looked like this. And if you look at these two cases, I mean, you should remember, you should be able to identify these two when they're side by side, okay? So if you look at overdamped and critically damped at the same, for the same mass and same spring constant, both of those, even though you can't see it very easily in the overdamped case, if you zoom in, both of those have zero slope at time equals 0. We required that, and both of them have a value of 0.05, which is just what I was using as my L. That's where it was released from at time equals 0. But you can see that the overdamped case is really smoothed out, and it takes a long time compared to the other case to get back to equilibrium. The critically damped case is back at equilibrium pretty quickly. Okay? So now we're going on to the one that's mathematically the most interesting. Although, you know, practically speaking, critically damped is really the key one. Okay, so now we're going to case 3, and that's underdamped. And that's the case where 4km is greater than c squared. Okay, and the thing that changes everything is when 4km is greater than c squared, you can see that this second term is imaginary. Okay? Okay, so I am going to start with, I'm going to define A as negative C over 2m. Okay, that's how I've been defining A this whole time. So that's that first term in the solution for lambda. And I'm going to define B. This is different now. This is going to be the square root of 4km minus c squared over 2m. Okay? Before, when we described it, because c squared was bigger than or equal to 4km, our b was square root of c squared. You know, we just flipped the two things in the square root. Okay? But now that we have this, okay, our two roots are going to be our lambda 1 is going to be, and this, I just wrote this wrong. I've always been calling this negative a, just to point out that this is always a negative number. Okay, so I'm going to keep doing that. And so lambda 1 is negative a plus I times b. That's the complex part. And lambda 2 is negative a minus ib. And the solution has a form x equal to, we have some constant times e to the lambda 1 times t. Plus some new constant c2 times e to the negative a minus ib times t. Well, you can see in both of these cases, you can rewrite this as c1 e to the negative at times e to the ibt plus c2 e to the negative at times e to the negative ibt. Okay, that's just what the meaning of those exponents is. That's the exponent rules. And now I'm going to rearrange this, and I have x as a function of time is equal to, I'm going to pull out the e to the negative at. And then we're multiplying that by c1 e to the ibt plus c2 times e to the negative ibt. Okay? And now is where the relationship between complex exponentials and trig functions comes into it. So this is Euler's formula. It says that e to the I times something, it doesn't matter what, let's call this e to the ic, okay, is equal to the cosine of c plus I times the sine of c. Okay? So we're going to use this. And notice that this means that e to the negative ic. Okay, so what's the relationship between cosine of c? So c is just some angle in radians. What's the relationship between cosine of c and cosine of negative c? Remember on the unit circle, so here's an angle, let's call this angle c. Bless you. So this would be negative c, okay? And let me change that a little bit. Okay, so those angles are both c. One's going counterclockwise, so it's positive c. One's going clockwise, so it's negative c, right? Using the unit circle, the cosine of that angle is the x coordinate. And so what's the relationship between cosine of c and cosine of negative c?
They're the same.
They're the same, yeah. So if you have a negative argument here, this is equal to cosine of, we can write this as cosine of c. And now let's think about the same thing with the sine. Using the unit circle, the sine of this angle is the vertical component. So when you compare the y component for the positive angle c to the y component for the negative angle c, what's the relationship there?
Inverse.
Yeah, and so this is just equal to minus I times the sine of c. Okay, and so now I'm going to plug this into our expression. And we get x of t is equal to e to the negative at times, so first, this one has a positive exponent, so this is c1 cosine of, what's the argument of this cosine if I'm using Euler's formula? Yep. BT, perfect. BT, and then plus I times C1 times sine of BT. Okay. And then now we're on this second, the C2 term. So this is the one with the negative exponent, so we're going to use the subtraction formula here. So we have plus C2 times the cosine of BT, and then minus I C2 times the sine of BT. Okay, well, we have some things we can group together. And then we can group these together. So we have x of t is equal to e to the negative at times, we have a coefficient of c1 plus c2 times the cosine of bt. And then we have I times the coefficient c1 minus c2 times the sine of bt. Okay? And now we're going to go to the boundary conditions. So the boundary conditions say two things, that when x is equal to, when t is equal to 0, x is equal to L. These are the same boundary conditions we've used in every case. And when t is equal to 0, x dot is equal to 0. Okay, well, let's calculate that derivative. So x dot is equal to negative a e to the negative at times all the stuff in the brackets. Plus, I'm just continuing that line down here, e to the negative at times negative c1 plus c2 times b times sine of bt plus I times c1 minus c2 times cosine of bt. Okay, and now we want to use the fact that x dot at 0 is equal to 0. So when x dot is 0, what do we get? and when t is equal to 0 also. So we have negative a times what's e to the negative at when t is equal to 0?
1.
Yep, 1, exactly. So I'll just write this as a. When t is equal to 0, what's cosine? 1. And so this is just, I'll just write this as c1 plus c2. When t is equal to 0, what's sine?
0.
0. So, okay, we have this for the first bracket. And then for the second one, e to the negative at when t is equal to 0 is 1. And then the second bracket, when t is equal to 0, the sine term is 0. And so we have, so that first term goes to 0. The second term, when t is equal to 0, cosine is 1. So we have I c1 minus I c2. And this has to be equal to 0. Okay. And let's see, I'll just, how do I want to write this? I guess I'll write it as A times the quantity C1 plus C2 is equal to I times the quantity C1 minus C2. Okay. And then I'll set that aside and go to the second boundary condition. So when time is equal to 0, x is equal to some L. And so I'll go back to this expression for x and plug in time equals 0. When time is equal to 0, that outer exponential goes to 0, goes to 1. And so we get to the inner thing. We just have C1 plus C2 times 0. No, I'm sorry. C1 plus C2, the cosine of 0 is 1. Are you with me on that first term? And then time equals 0 makes the sine 0, so this one just goes away. So all we have left is that C1 plus C2 is equal to L. Okay. And so C1 plus C2 is equal to L. So now we can say AL is equal to I times C1 minus C2. So C1 minus C2, well, I'll just leave it like that. And so now we can go to the function x of t. We can add these updates, and we have e to the negative at times, here's our expression for x, C1 plus C2 is equal to L. So we have L times the cosine of BT. Then the second term is I times C1 minus C2. That's equal to AL. So we have plus AL times the sine of BT. Okay? And so what you get is a sinusoidal function that decays according to this negative exponential. Okay? You see, like the shape of that negative exponential, this is, you can think of this as the decay. Because by itself, this has a graph that looks something like this. Okay? And so altogether, this comes out to be like that. Isn't that cool? And depending on how much damping you have, how quickly this thing decays, you can have something that looks very much like the undamped case or something that looks very much like the critically damped case. Okay, let's look at that for a second. So let me pull up this spreadsheet. Course notes. Okay, so we'll go to underdamped. And this spreadsheet, this is M and this is K, right? And this is C. So if we want to see something that's very close to the undamped case, we'd make this damping coefficient really small. You can see that C squared in this case is way, way less than 4 km. And what you see is essentially an undamped harmonic motion. It's actually decaying a little bit, but so little you can barely see it. Okay. If we wanted to see this behave very much like the critically damped case, what number would we want to make this C equal to? Yeah, well, so we would want it to be very close to, remember, the key thing is that C squared is less than 4 km. 4 km is bigger than C squared. Okay, so 4 km is 4 times 1 times 100, so 400. So if this is just under 20, we're going to see something that looks like the critically damped case. So let's make this 19, because 20 is the square root of 400, you know. And there, you can't see the oscillations. It just looks like the critically damped case. But let me do one where you can start to see the oscillations. I don't know what that would take, but let's try this. Okay, you can see as the damping gets lower, it tries to oscillate a little bit, but it's not visible at this scale for very long. Okay, it really is oscillating, it's just oscillating very little. Make it 10. And little by little, you're starting to see those oscillations come in as it goes from the critically damped case to the underdamped case. That's cool, right? Now you can start to see that third hump, you know? Any questions about the sort of overall, these three overall cases? Okay. There's one more thing that you have to know about this. And that is that damping so notice the damping reduces the frequency of oscillation. Remember taking this oscillator and hanging it and letting it oscillate didn't change the frequency. Putting it at an angle didn't change the frequency. But the damping does reduce the frequency, and this is how you can see it. So the frequency of this oscillation, okay, so the period first is, we can calculate by saying so B times tau is equal to 2 pi. Okay, and B was equal to square root of 4km minus c squared all over 2m. Okay, so tau is equal to 2 pi divided by b, so that's times 2m over square root of 4km minus c squared. The frequency is just the reciprocal of this, so the frequency is 1 over 2 pi times the quantity 4km minus c squared over 2m. Yep.
In the second step there, is the 2m supposed to be under this?
No, it's not. Thank you. Okay, so let's compare this now to the undamped case. That was frequency is equal to 1 over 2 pi times the square root of k over m. Okay, and so we're just comparing, you know, how does this thing relate to this thing? Well, notice that square root of 4km over 2m is equal to 2 times the square root of k over 2 times the square root of m. Okay, so that's just equal to square root of k over m. So when we subtract this c squared, inside that square root, it just simply reduces the frequency from the undamped case. Okay? Any questions about that? Yeah.
Yeah, I'm just a bit, I guess, confused about the square roots here. So in this part, it's square root of k over m, and then on the left there, is that square root supposed to be over the whole equation?
On the,
Or k?
so, okay. Tell me when where.
Down, yeah, that.
Okay, so here it's not over the, okay, here it's only over the top. But now we have a, you know, a square root of 4 times the square root of k times the square root of m.
Mhm.
Okay? And the square root of m over the m
I just saw
gives you a
it.
square root on the bottom, yeah.
Okay. Thanks.
Any other questions about that? Okay. What do I want to do? Let's, in the last 10 minutes, let's just do a derivation of the, so I'm going to give you time to work through a derivation of the undamped case, the simplest case, okay, just so you can sort of get used to putting these pieces together. So let's say that we have a harmonic oscillator. I'm putting it like this, but the calculation would be exactly the same if this was a hanging mass that was oscillating up and down or whatever. And let's say this is 0.2 kilograms, and let's say that K is equal to 300 newtons per meter. And we want to derive a general equation for x of t. And what I mean by the general equation is, I don't think we have time to go through the boundary conditions, but we're just going to come up with a sinusoidal expression. Okay, so we're not going to go through the boundary conditions. Okay, so what's the first step of this derivation? One answer you can never go wrong with in dynamics. Yeah, exactly. Draw a free body diagram, yeah. So start with a free body diagram and then use that to go to Newton's second law first. okay? Okay, so the free body diagram, you have some vertical stuff that isn't going to end up mattering. So that's 1.962 for the weight, a normal force. And then the direction of the spring force, I'm going to draw that in the positive axis direction. In this case, that's positive x. And call it negative kx. So this is going to be negative 300x. Okay? And then Newton's second law, well, you can write out the full equation or just write out the x component. I'll write out the whole thing. So 0, negative 1.962 plus 0n plus negative 300x 0 is equal to the mass, 0.2, times the acceleration that's only in the x direction. And so the x equation says negative 300x is equal to 0.2, and the acceleration is x double dot. Now combine these two and you get x double dot plus 1500x is equal to 0. Okay, so that's the governing ordinary differential equation. So after you have that governing ordinary differential equation, what's the next step? So now we're going to assume the form of that x. What's the form we're going to assume here? We're going to assume that x is equal to some constant, call it C1, times the cosine. And then the last thing we have to do is figure out the argument for that, both of these trigonometric functions. So what's the argument going to be? Well, you know that two derivatives, two applications of the chain rule, has to give you a coefficient of negative 1500. Okay? Since it's two of those, we're going to use the square root of 1500 and multiply it by t. So now you can see if you take two derivatives, you end up with negative C1 times 1500 times cosine. Okay, and then we'll do the same thing with the sine. So C2 times the sine of square root of 1500 times t. And so now what's the frequency of this? We don't have to use the boundary conditions. So this is the general solution. And now we can say that the frequency is equal to 1 over 2 pi times the square root of 1500. And we get a frequency of 6.16 hertz. This is a pretty small mass and a pretty stiff spring, so this thing's vibrating pretty fast. Okay? Any questions about that? Okay. I I think the problem I gave you was related to that in some way, right? I think deriving that undamped case. And so if we had damping on this, you know that if it was underdamped, so it still had the oscillations, you know that the frequency would start at about 6.16 at very low damping and then get slower from there. Yep.
To get the like the C1 cosine
Yeah.
BT, would we just go back through our notes and find that in our?
To get that, I would say you probably want to understand how to apply those boundary conditions, you know? So remember, to apply those boundary conditions, you'd say, okay, our two boundary conditions, like they have been all the time here, have just been, they're sort of like our default boundary conditions. We'll say that x at time equals 0 is equal to L, and x dot at time equals 0 is equal to 0. You'll start with this form, apply these two things, and that'll let you calculate C1 and C2. Okay. And then if you ever forgot that frequency formula, remember the way you can get the frequency is you know that the period comes from setting whatever is in the trigonometric arguments equal to 2 pi and then solving for t. And then the frequency is the reciprocal of that.
And we don't have to like derive the cosine of square root of k over that.
No, it's enough to just be able to, remember you can just write down what you think it is, what you think you remember, and then take the second derivative and see if it works. You know what I mean? If you think of it right, when you take the second derivative and plug the second derivative and your expression for x into this equation, you'll get 0. Okay? So, I mean, it's always enough to just get lucky. You know, in this case, you can just think of it as like, oh, I thought of something that worked, I got lucky. But once you have it, you can check and make sure that it holds. Okay, and then, so we'll do some oscillating systems, like dynamical systems on Wednesday and Friday. Okay, that's all.